It's a great pleasure here to be here and to give actually the first talk in the celebration of my good friend Samson's 60th birthday. I first met Samson, I think it was 1989, and this was in a very interesting, different universe, so to speak. It was a time where we had still the Soviet Union, and he was one of the delegations of a Soviet Union string theorist was visiting the US, and they were visiting in a few sites, and Harvard, we were lucky as one of those. And he came with a few other very good string theorists, young string theorists, describing the work they were doing, and it was quite interesting to get to know them at that time, and that was the beginning of my knowing Samson. I even remember roughly what his talk was about the WZW and some aspects of the WZW models, which actually is somewhat related to the talk I'm going to give today as well, some aspect of it. And then I met him more and longer and actually collaborated with him on a couple projects. And this was in 1994 when I was a visitor, I guess, on sabbatical leave in the Institute for Advanced Study. So at that time, Samson and it was always great pleasure talking with him, and we always had fun talking about various things in physics, nothing necessarily focused, but just general discussion. And I always find it inspiring to talk with him. He had always open mind about all these different aspects of physics, and always brings some interesting insights to the discussions we had. And so we began discussing, things that we found interesting, and gradually went to a particular direction. I still don't know why. We started working on exceptional conformal theories, and in particular spin 7 and G2, which almost nobody was interested in. So it was kind of a bizarre subject. We just find it fascinating that there are these kind of things that could be possibly true, and nobody had studied that seriously in the context of string theory. So we just said, let's study it. So again, this is the open mind that he exhibited in terms of his interest as well as ability. It involved an amazing amount of talent, which I certainly lacked, and he had in terms of understanding amazing properties of this new algebra that we were finding in 2 dimensions. And that was quite a fun collaboration I was happy to be part of, and it led to 2 papers. And since then, we have collaborated not necessarily in papers, but in discussions in different ways over different places, and most consistently during the summer workshops in the Simon Center and so on. We have been talking, and I have had the great pleasure of continuing my interaction with Samson. So on this occasion of his 60th birthday celebration conference, I'm going to talk about basically trying to do these 2 themes that I've also been interested in, and Samson is a master in, and one is the subject of anomalies. And this is going to be an overarching theme in my talk, as well as some aspects having to do with supersymmetry, which is again another domain of his expertise, namely in particular N=2 supersymmetry, and his work with Nikita on this area has impacted quite tremendously the subject, especially in the connection with integrability and integral models, the deep insights that they found in connecting these 2 fields. So that's the basic introduction, and I want to then get a bit more focused. I'm going to talk about works which is related to some joint work I've done with Hee-Chul Kim and Gary Xu and Huri Tarazi, as well as, if I get a chance, I hope, with my student Jacob McNamara on a different work. So my main focus is going to be these series of works, and if I get the chance, I'll briefly also mention this other work. So to set the stage, I have to tell you the basic kind of a place where what I'm going to talk about fits. And this is the idea basically about what constitutes a good quantum gravity. And there was this belief that you take a quantum field theory and you just put a metric, couple it to the metric, and make the metric dynamical, integrate over metric, and then you have quantum gravity. And this was good on paper. It sounded good. And the problem was when already long ago Feynman and others started looking at this, it gave infinities, and nobody could make sense out of it. So the conclusion then was, we don't know how to do it. Of course, it should be possible because we live in a theory with quantum gravity. So they didn't figure out, but there should have been a solution. And string theory, of course, came up with a solution. Somehow it works now in the context of quantum gravity. And so we celebrated in string theory that quantum gravity is great and we can solve it, it's finite or it makes sense, there's no problem, and we're done. Well, actually not so fast. And in fact, what we didn't appreciate so much in string theory, especially the early days, is how special string theory ends up being. And in some sense, Feynman and others were essentially correct, that quantum field theories cannot be coupled to quantum gravity consistently. That was the message that Feynman and others originally drove, and that's almost correct. There are a few exceptions, and those are the exceptions that string theory comes up with. So in some sense, we should view string theory as providing loopholes to this idea that quantum field theories cannot be coupled to quantum gravity. So I'll try to illustrate this point in my talk. So I start with, I first focus on supersymmetric theories. So supersymmetric theories coupled to gravity are, of course, the better chance of understanding, because in the supersymmetric theories, we have less quantum corrections, at least certain quantities are protected. So we have a backbone of the theory is forced and it's protected, so we have a better understanding of what we are doing. So it's the best place to start understanding coupling to gravity. Start with a more restricted case, which is more symmetric. So what we seem to find is that in the context of supersymmetric theories, we have, when you couple them to quantum gravity, if you try to see which kind of supersymmetric system you get, you start with a quantum gravity theory coupled to some matter. You go to low energy, and then you ask what quantum field theory you get. So there's a projection from quantum gravity by taking the low energy limit to space of quantum field theories, and you can ask what kind of map this is. Is it onto? Is it how big? How much do you cover the space of quantum field theories? Of course, we believe the space of quantum field theory is infinitely big, especially even supersymmetric ones. We have a huge number of them. For example, n equals to 4 Yang-Mills in 4 dimensions is a finite theory for every gauge group. For every group you choose, it's a unique theory. So we think it's a huge infinite many possibilities, but it's not clear what the image of this map is. In fact, what we have been learning, at least in the context of supersymmetric theories, that this image is finite. Not only it's not onto or anything, it's far from it. It's just a finite image. So this is what I want to basically point out, that we really have just a bunch of points in this infinite space of possibilities that are consistent with quantum gravity. And this point that essentially everything we are doing in the space of would-be quantum field theories only allow a very tiny subset, which is this what we call the string landscape, compared to the infinitely many other possibilities which are not realizable in quantum gravity. So this is what we call Swampland. The Swampland, even though it sounds like the name which suggests negative feature, it is negative feature as far as gravity goes. But as far as quantum field theory goes, it's perfectly fine. So these are good theories, like n equals to 4 Yang-Mills for any gauge group is good theory. And as I will argue, essentially all of them are in Swampland. So the ones that are actually couplable to gravity are very rare, very rare. So why do we have such an image? Well, we don't have a full definition of the theory, so I'm making a strong statement, a very strong statement, based on what? Well, based on constructions in string theory. Now, what are the constructions in string theory? Well, we take, if you're interested in a Minkowski vacuum, we start with some higher dimensional theory, 11, 10, and so forth, and you put it on a Calabi-Yau, and you get a theory, and depending on which Calabi-Yau dimension you choose in different dimensions. Well, you can have different choices, but no matter what you do, if the number of Calabi-Yau is finite types, then you will get finite number of possibilities in lower dimensional theory. There is no proof mathematically that the number of Calabi-Yau is finite. So if indeed that's infinite, then that would be against what I'm saying. So this finiteness is directly related in that class to the statement that there are a finite number of Calabi-Yau. At least if this is not finite, it will give you counter statement to what I'm saying. There's no proof, so this could be false, and it would be interesting to start verifying or proving or disproving it. In dimension 1 and 2, it's clearly finite. It's 1 in dimension 1, elliptic curve. And dimension 2 is only K3 or T4, depending on how much holonomy we want. Calabi-Yau threefold already, we think is finite. We don't have a proof. Yau conjectured it many years ago. And we have evidence for it. What's the evidence? Well, trying hard and not being able to. That's one evidence. But there's better evidence. If you take elliptic Calabi-Yau threefold, it has been proven to be finite. So we have further evidence that at least in the elliptic class, it is finite. And it seems from all the experiments people have done in trying to construct it that essentially, not all, but most of Calabi-Yaus are elliptic anyhow in the context of elliptic threefolds. And therefore, it's a good guide, we believe. So this finiteness criteria seems to be a deep idea. So in some sense, gravity is finite. Now, I don't want to mislead you by my drawing just 3 or 4 points. It could be 10 to the 10 points. My main point is that it's finite, not necessarily small number. But finite is finite, is compared to the infinite set is measure 0. So that's already quite a remarkable statement. Okay. Now, I have to contrast this just to make sure that I'm not misleading you. When we talk about a particular gravity theory, we also have defects, like branes, membranes, and this and that. And on those objects, we could have arbitrary number of interesting structures. For example, in 10 dimensions, type 2b, we can have arbitrary number of D3 branes, which you stack them on each other, and you get n equals to 4 Yang-Mills. If you have n D3 branes, you get UN Yang-Mills theory on it. There's no bound on n. You can have arbitrary big N. Infinitely many possibilities. So that sounds like a contradiction with what I'm saying here. So just let me make clear what I mean when I say finite. I mean finite number of theories for which the objects couple to gravity in that same dimension. So if you take n equals to 4 Yang-Mills on D3 branes with infinitely many D3 branes, they couple to 10-dimensional gravity, but not to 4D gravity. Gravity is not localized to 4D. Okay? So the gravity can go back from the brane and back to itself. That's fine. So what I'm talking about is that there are a finite number of gravity types of a given theory. Of course, there are infinitely many defect types. That I'm not talking about. So that should be clarified. So indeed, it should be, because we believe, in some sense, all quantum field theories should be observable or constructible in string theory. And since they're infinite, you should be getting it through defects in string theory. That's all. But if you want to get a quantum field theory in a given dimension, you better start with gravity in a higher dimension in order to do that. Not in that same dimension. If it's in the same dimension, you're going to run into trouble. Okay, good. So that's, I think, a basic point. Now, so how do we assess this program? You see, the program of trying to use string theory to come up with this principle is a little bit strange, because, and it's subject to criticism in the following way. We don't have a principle of what quantum gravity has to be. We just have learned some basic facts, but we don't have an overarching definition of what quantum gravity is. So if we just study string theory, then you're subject to the criticism like you can only understand things which string theory can construct, not a general quantum gravity. That's a valid criticism, and that's the lamppost principle, the lamppost problem. You only study what you can, and string theory might be just a tiny little corner of what is possible, and the whole vast thing you cannot. And so, yeah, maybe we are just being misled by string theory giving us these few points, but the whole thing is actually constructible in some other way. Okay, that's a valid criticism. If we want to actually understand whether or not it's true or not, we have to use some principles that we have learned and understand it beyond string theory, and use those principles to actually get insight about what is allowed and what's not allowed, and see whether with those principles would you still get only these points, or there's more to the story. So in other words, we should be able to assess the principle of lamppost principle based on principles we are learning from string theory, but can be derived with the ways more general than string theory. That's, I think, the basic aim of this program, to try to connect this to a more basic idea of consistency. And what do I mean by more general or more basic principles? Things like consistency of black holes, things like unitarity of the theory, things which we believe has to be true in any quantum gravity, not specifically about string theory. So using those facts to see if we can say anything which is beyond this. Good. So let me start then with the supersymmetries. So the highest amount of supersymmetry is, we should always start with the highest one, is a theory in various dimensions which have 32 supercharges. There are different types and different dimensions, but the biggest number of supersymmetry you can have are 32 supersymmetries, and the highest dimension is 11 for this. But you can have less, and you can go down. Of course, you can take the one with 11 dimension, which is the usual M-theory definition, and you compactify on tori, and you still get the same amount of supersymmetry. But there's also another class. So the non-chiral ones are just, you can obtain them by a toroidal compactification of the highest one. So this gives you the less than 11 ones. But there's also a chiral one in 10 dimensions, which has 2, 0 supersymmetry. So these are basically classification, nothing to do per se with superstring theory or anything like that. It's just a supergravity statement, representation theory. Okay? So if you don't know anything about string theory, and if you just study supergravity theory, you find, well, there are only two possibilities, either the one which is in 11 and the other ones which could be related to circle compactification or something in 10 dimensions. It could have been that string theory got neither of them or one of them. Well, string theory luckily gives you both of them. So this is already the beginning of a good situation, that what seems to be consistent is constructible in string theory, and it's one-to-one. So we can check this off as saying, okay, so this set of possibilities with 32 supercharges is very limited, but nevertheless, all of them are constructed in string theory. So the string lamppost principle in this case succeeds to give you everything that is allowed. Okay, good. So we now begin to get confidence, perhaps, that everything which is allowed maybe can be obtained from string theory. So let's go to the next case. Theories with 16 supercharges. How many of them are they? Well, this again, there are two classes. It's chiral and non-chiral theories. The chiral theories only appear in dimension 10 and dimension 6. And actually, there could be intermediate supersymmetries like 24 and so forth, depending on how low a dimension you go. I'm interested in higher dimensions for now, so let me just restrict to 16. Dimension 10, you can have 1, 0 supersymmetry, which is chiral. And dimension 6, you can have, again, a 1, 0 2, 0, what's called in 6D theory, which is, again, has 16 supercharges. And the non-chiral theories, you can have anything with d less than 10. Again, I'm not using string theory here. I'm just using classification of supersymmetric theories. Low energy description gives you these possibilities. More than that, anomaly cancellations, these theories are anomalous, so anomaly cancellation will tell you the only possibilities for gauge symmetries in this theory is E8 cross E8, or SO32, or E8 cross U1 to the 248, or U1 to the 496. There are only 4 possibilities. In this case, the theory is a theory with certain number of tensor multiplets, 21 tensor multiplets with a symmetry structure which is locally given by SO21 of times 5, SO21 comma 5 divided by SO21 times SO5. And this is an anomalies fix the structure of this tensor multiplets and so forth in this theory completely. So these are the only possibilities here. For d less than 10, you find is perfectly fine with arbitrary gauge group G. For all G, it looks fine, possible. An example of this d less than 10 is that in 4D, n equals to 4 Yang-Mills, for example, supersymmetric n equals to 4 supersymmetric Yang-Mills is consistent with any G, and in fact we believe is finite theory. So UV divergence is cancelled because of such a high supersymmetry in 4D. So this is
because these ends are very different. So
yeah, this is the n and this is the curly n. Okay. So this is n is the total number of supercharges, and that is So it doesn't distinguish which dimension you're in. And this is just assuming packages them in terms of the spinor of that dimension. So four of four-dimensional spinners. 4 times 4 is 16. Okay, so that's basically the structure. Okay, good. So now we can see whether the lamppost principle works. Luckily, these two have been constructed. The hydraulic string constructs both. One of them is actually also can be constructed using type 1. But these two are not constructed. So originally, when Green and Short found this anomaly cancellation and found this example, they believed that this is a good string theory. They found this type 1. They didn't know at the time that they constructed that there's this other one, and they thought there must be a way to get this. Lo and behold, hydraulic string realized that. So that was a beautiful confirmation of string lamppost principle. It did not have to be constructible. It was constructed. But there were two other cases that was not constructible in any way. And maybe they said maybe for some reason it's not allowed or something. Okay? So they conjectured or they asked whether or not these make sense. So there has been work, and I will mention the work we did, which shows that these are inconsistent theories, despite the fact that anomalies cancel. So in other words, with this much supersymmetry, the only consistent theories are the ones that string theory gets. Again, string lamppost principle is complete. That meaning anything which is consistent is realizable within string theory. D equal to 6, this theory, again, it is complete because this is simply type 2b compactified on K3, and that's the only way you get in string theory. Well, there's another way you can get in string theory, which is M theory on T5 mod Z2, but anyhow, they give you the same theories, they're dual to each other. So there's a unique theory with this much supersymmetry, and that's it. And so this, again, is consistent and is constructible in string theory. How about this class? Well, let's start with the first one, d equals to 9. D equals to 9 is the first puzzle case. You see, up to now, I have been using such a high amount of supersymmetry or chirality, anomalies, which is one of the powerful tools in quantum field theory, to restrict the possibilities, and maybe I ruled out two boring, funny cases, as I will explain how. But in d equals to 9, the dimension is odd. And so the chirality and so on is not there to help us. And in fact, naively, you would think there are infinitely many g's possible. Can you get every g? There is no problem with quantum gravity, at least naively, when you write it down. It seems to make sense for arbitrary g. Now you ask, okay, can string theory give me everything? Unfortunately not. It only gives you theories which rank, the rank of the groups being 17, 9, and 1. Only 3 possibilities. So if the rank of the group is one of these 3 ones, in principle you can get them in string theory. I'm not saying every theory with these ranks you can get, but at least it has to have this property. But naively, the theory seems to be okay with arbitrary ranks. So what happened? What are these theories? Rank 17 is obtained by simply taking these theories and putting it on a circle. You get an extra U1 by the circle. So that gives you the rank 17. The rank 9 theories can be obtained from this E8 cross E8 theory if you put it on a circle and exchange the 2 E8s as you go around the circle, and that gives you rank 9 by the outer automorphism of this theory. This is what's called the CHL string. And the rank 1 theories cannot be obtained from hydraulic string. So one might have thought that this is bizarre. Why do you get rank 1? This you get from compactification of M theory on Klein-Bottle. So you have to use all these ways, and somehow you can get them. So you get all these 3s, but you don't get arbitrary rank. That's the only 3 you get. So the question is, are we missing something? Is string theory missing something? Or indeed, that's the list? If this is indeed the list, or there's some restriction like this, then you begin to feel that, maybe we should be just studying string theory and there's nothing else. And therefore, we can trust the lessons we are learning from string compactification in trying to draw general lessons about quantum gravity. I will talk about these cases in a second, but before I do that, I will also want to talk about the next case. The n equal to 8 case And this n equal to 8 case, which is in 4 dimensions, it leads to n equal to 2 supersymmetry in particular. So this is the same class of theories we're talking about. And that's the class that Samson has worked quite extensively on various aspects of it. So this is the next case. And in the n equals to 8, again, you can have a chiral ones and non-chiral ones. Chiral one starts in 6D. Well, it is in 6D, and it has supersymmetry, which is 1, 0, supersymmetry. And non-chiral ones can be, for example, viewed as compactivation of this on the circle. So you can 5, 4, etc. You can just compactify this on a circle, and you get theories with 8 supercharges. This is one of the well-studied cases, for example, in 4D or 5D, by compactifying M theory on Calabi threefolds and so on. This is this class, so it's very well studied and so forth. And the 6D ones can be obtained again by Calabi threefolds. In this case, you use F theory on elliptic threefolds, and again, you get the same class of this type. Now, again, this theory, this part has anomalies in it. And again, anomalies play a key role in trying to constrain the theories. But unlike the 10D case, and unlike the 6D case with 2, 0, anomalies are not nearly as powerful. In fact, you get infinitely many possibilities which cancel anomalies, as was studied by Taylor and collaborators. So there's a huge number of possibilities, but only a finite number of them can be obtained in string theory. This one actually has been proven in the sense that elliptic Calabi threefolds, which is the way we get these theories in string theory using F theory, have been proven mathematically to be finite. So we know there's no more than that we can get in string theory. It's finite. But anomalies give you an infinite set. So if anomalies is the only guide, you should get infinitely many possibilities, and yet we get only a finite number of them. Okay, so these are the things I want to basically focus on, but so let me start with the 10D story first. Let me see where would I. Oh, there's a board behind this. Okay, good. Okay. So let's do the 10D case. Sorry. Oh, I see. Very good. Thank you. Excellent. Thank you. Okay, so let's talk about D equals to 10 case. And in this case, the anomaly cancellation actually came up with an extra equation, which is the fact that dH is not 0, but given by trace of R wedge R minus trace of F wedge F, with some specific coefficients and so on, where H is the field strength corresponding to the B field. And this is quite interesting because of the following fact. So this comes from a B field, and this is telling you that there is some source for the B field, the field strength of it, and usually the right-hand side should have been 0 if B is equal to dH, but there's these Chern-Simon terms that come up in the definition of the H, which gives you the D of it is not 0, and you can compute these statements. The fact that there's a B mu field means, in the context of quantum field theory, that if you have a 2 form, you could have a 1 + 1 dimensional object which couples to it, a string. Now, in the context of whether or not this is fundamental string or what string, I don't even have to talk about it. We know there is a string. How do we know there's a string? There could be a 1 + 1 dimensional, the 2 form, but nothing couples to it. That's not possible. In quantum gravitational theories, every charge that's available is occupied. The spectrum is complete. So this is, how do I know that? How do I know that in a quantum gravity theory the spectrum is complete? So for example, if you have a U1 gauge theory, you can have a Maxwell theory with nothing charged. That's fine as a quantum field theory. But as a quantum gravity, you cannot have a U1 with nothing coupled to it. Why do we know this? This is basically Hawking's black hole computation. You take a black hole of a given charge, you compute the entropy, you find it's not 0 for any charge. And therefore, for every charge, it's occupied. Now, you might say, well, this is only applied to big black holes and so on, only for big charges. But you can take a big charge and a big negative charge minus 1, and you put them together, you get something with charge 1. So therefore, every charge is occupied in a quantum theory of gravity. So that's a very strong statement without doing anything. This is not because of string theory. This is, again, consistency of interpretation of the black hole and the black hole entropy. So if it's complete, there's some string coupled to this. And in fact, you can get an idea about what kind of strings you can have. And in this particular case, you can actually preserve supersymmetry. You can have supergravity solutions which preserve half of the supersymmetry. So we expect there to be a string with 1 plus 1 dimension, in other words, 1 plus 1 dimensional defect with 0, 8 supersymmetry on this defect. So this should exist. I am not using string theory. I want to emphasize. This is not using string theory. This is simply using the fact that there should be completeness of spectrum. Okay, so if there's a theory with 0, 8 supersymmetry, what does this tell you? Well, as is well known, and this is the kind of things that is this domain of expertise of Samson, is the anomaly inflow. And in fact, we will hear something later after my talk from Rubin about the similar story for the M5 brains. This equation tells you the anomalies that have to live on this string just from this equation. So this equation is smart enough to know something has to live on the string. What does it tell you? Well, from this term, you learned something about C left minus C right on the Pontryagin class of this string. So you learn C left minus C right is 12. After you take into account normalizations correctly, I haven't put numbers there, but if you check it, you find it's this. But there's something else you learn from here. You see, if you look at a string, the transverse to the string is an SO8 degree of freedom. There's a rotation degree of freedom on the string, transverse to the string. But there's also the tangent to the string, so you can decompose the tangent to the tangent along the wordsheet of the string and the tangent bundle normal to the string. And from this, you find, in other words, if you decompose this to something like the Pontryagin class of the wordsheet plus the second Chern class of the SO8 related to it. From this, you learn the fact that there's a 0, 8 supersymmetry and the fact that the SO8 is related to that same SO8 symmetry. You learn the central charge of the right movers because there's a relation between the anomaly coefficients in the current of the SO8 and the central charge. So you learn C right, basically using that, you find C right is 12. And therefore, this equation simply gives you C left is 24. Now you use the unitarity. Now you use the fact that this coefficient here is not 0, which means that every gauge group in the bulk should be giving you a current algebra with a non-vanishing level on the wordsheet. And you can find this left mover. So you find that the central charge, due to the current algebra, should be less than or equal to, what can it be? It should be less than or equal to the dimensions that correspond to the unitarity of the conformal theory. Now, the left movers has 24. There are 8 transverse motions that you can put the strings on. So you can have to, if you subtract and see how much central charge you have at your disposal, you find 16. So you find the central charge of the group should be less than 16. But WZW construction tell you that the central charge is always bigger than or equal to the rank of the group, namely the U1s. And therefore, you learn that the rank of the group is less than or equal to 16. You look at your list, and indeed, you find there are 2 rank 16s, and these are out because they are more than rank 16. You're done. So this is telling you that simple ideas having to do with anomaly inflows, unitarity, and the existence of this object is putting you strong restrictions on quantum theory of gravity. Something which would have not been obvious if you just studied the low energy supergravity. Okay.
But this again follows completely from anomaly.
Completely from anomalies.
Completely.
But the anomalies in this case involves the anomaly inflow on an object you may not have studied a priori. You may have said, in other words, you could have said, this object may not exist, in which case there's nothing to talk about. So I'm using a little more than anomaly. I'm using the fact that this object exists, it has this supersymmetry, and then there's anomaly inflow on this and unitarity on it. If there's not unitary, there's no problem, and so on. So I'm using a few more ingredients: unitarity, existence. So it's a few more steps, but all reasonable. So that's what I mean. So we're going beyond just assumptions of string theory, but assumptions which are reasonable, unitarity and completeness. Again, so we learned that string theory does not miss anything in this case either. Let me just, I think probably the up one is what I want to bring down. I like this. This gets stuck here. Little finesse. Yes, I see. Let me see if I want to push this up or not. Oh, better not. I was about to jump up there. Yeah, it's very nice. You do your exercise here. It's actually interesting if somebody asks a hard question.
So I should move back.
No, don't worry. Today, no, not today. Don't worry today. You're okay. Okay. I think I should go a bit faster. Let's see. So, okay. So now we come to the next case, which is d equals to 9, and theory has 16 supercharges. How about this? There's no anomaly. Nothing. There's nothing. You have no choice. What can you use? Well, you still have a B mu field. And in fact, this is true for 8, 7, etc. So for all of these, I'm not saying just 9, 8, 7, etc. There are all these cases. And you can study what happens in these cases. Well, before we study what happens in these cases, let's continue our geography of what we get in string theory. I said over there that you get in 9 dimension rank 17. You got rank 17, 9, or 1 for the rank of the gauge group. These are constructible in string theory. In 8 dimensions, you get ranks 18, 10, and 2. In 7 dimensions, you get ranks 19, 11, 7, 5, and 3, and so on. In d equals to 4, which is the n equals to 4 case, I don't know the full list, but it starts with 22 and goes down. So this is what examples of the ranks we know. And naively, quantum n equals to n in theory with 16 supercharges predicts that you should have arbitrary gauge group. Nevertheless, these are the only ones you realize in string theory. And these, especially these odd ones, clearly there's no anomaly, and these even the even ones don't have it. So therefore, there is a bizarre situation. They have no control. The anomalies don't seem to be useful anymore. But actually, anomalies again run the show, as I'll try to explain. Here we need a few more ingredients. So again, there's a B field, and therefore again there's a string. But could the string be chiral? Yes, it has to be chiral because the supersymmetry on it is again the same amount, 0,8. These follow from just studying the BPS string. Conditions on BPS supersymmetry, you find that there's left and right supersymmetry 0,8 on the string. What about the anomaly inflow? Well, now if you look at the equation that you had before, you find that the coefficient of R wedge R term is not fixed anymore by supergravity. But the coefficient of F wedge F term is fixed by supersymmetry. So supergravity tells you that all the gauge fields should give rise to a current attribute at some level. But we don't know anything about the C left and C right a priori because there's a coefficient there is not fixed. Gravity, supergravity is not smart enough or strong enough to fix this. So this we don't know about. So here you see, for the theories, the 9, 8, 7, etc., even though the theory is not chiral, there is a chiral object. And therefore, it does see anomalies in principle, but we don't know what the anomaly has to be. Unlike the situation in 10D, where the coefficient here was fixed to be 1. Well, in this case, what you find, again, doing the same exercise as I did before, you find that C right is 12K, or kappa, whatever I call it there. And C left minus C right, again, is 12K. So K equals to 1 was the case we had before, and now we have this situation. And in principle, K can be arbitrarily large. And so therefore, if K is arbitrarily large, there is no restriction on here. And so we would not be able to restrict anything. Except, now here I want to use a principle, which is one of the things that has emerged from Swampland, which is called the distance conjecture. Distance conjecture in the Swampland states that if you take any theory of quantum gravity which has some scalars fields coupled to it, which gives rise to some kind of a moduli space, if you go far enough in the field space, you will get a tower of light states. So for large enough phi, you get a tower of light states emerging exponentially fast. So the mass, the tower comes down to 0 mass. And what are the meaning of these light states is a dual description of the theory. In other words, the distance conjecture basically quantifies what we mean by duality. That is, no matter what you do, you always, whichever corner you go, you get a different description at infinite far away. A new description, which is weakly coupled in not necessarily the same form, in a dual language. So I'm going to assume this is still the case. That is, that anytime you have a parameter in your theory, if you go to infinite distance away, you get some dual description. I won't assume what dual description, just some dual description. So I will use this fact. So this fact is an extra ingredient I need to get going in these cases. Assumption that there is a duality. Okay, so if you do this, how does this help you? Well, the idea is the following. If you take a theory in d dimension, and if you look at the moduli space of these theories with 16 supercharges, you get some theory which has something, some kind of an Orion lattice of some kind, with charges as well as the moduli space. So you have something SOM plus k times k, k with some particular n's and k's. This is what we know. This structure follows from supersymmetry, not string theory. So supersymmetry tells you it's like this. Okay, the scalar moduli that you have is like this. But then what I'm going to do is I'm going to compactify this on an extra circle. I compactify the theory on an extra circle, and again you get an extra, again by supergravity you find that this extra circle at least gives you an SO11 piece. Of course, if you turn on Wilson lines, we'll mix with these, as we well know. But again, I'm not using string theory. I'm just using supergravity.
Are you assuming T-duality here?
I'm not assuming.
No, it's a T-dual group.
No T-duality. I'm just assuming that you compactify it on a circle. The fact that there's an SO11 comes is just follows from supergravity description. Now I'm going to use the distance conjecture to argue there must be T-duality. So I will explain it in this form. So if you use this, there's a moduli for SO11, which is the radius of the circle. If you go to the 0 radius, this is infinite distance away, and there must be a dual description. The dual description should have 16 supercharges, and it must have, this is D by the way, it must have at least this D SO symmetry, and therefore it must be a theory which has a supersymmetry of a higher type of the same form because of this moduli space. So therefore you learn that there must be a theory in the same dimension D which has n equals to 16 supercharges, which compactifies to give you this one. In other words, there is a T-duality, namely the momentum modes of this new theory is related to something related to this other theory as the radius goes to 0. Which descriptions are they? There are strings in this theory. As I explained, there's a B mu still. Therefore, there are strings. And you can show by this much supersymmetry, they don't get any correction to their mass and all that. You can compute exactly what their mass is and their tension. So as you shrink the circle, the string wound around this, which is the BPS string, becomes massless, arbitrarily light state. And that must be the dual description of this other theory. That's what we call T-duality. T-duality is exactly the fact that the winding modes become the momentum modes of the dual theory. So therefore, we learn that there must be some dual description. We don't know what. It may be the same theory, it might be a new theory, but there must be a dual state such that the winding modes of this string get exchanged with the momentum modes of this other string. Okay. So this is part of the distance conjecture. But does that help us? How does that help us? It helps us for the following reason. You see, this theory, which has this k here, and the right mover, which has a central charge given by 12k, gives you a bound on the spin of the states. Namely, as is well known, for example, in the superconformal theories with n equal to 2 supersymmetry, there's a maximum charge which comes from the spectral flow of the theory. And we know that there's an upper bound for the spin of the states of the U1 in the conformal theory, which is given by C over, in the Ramon sector, is given by C over 6. And in this case, using the integrality, or in this case, the half integrality of the spin, because you can argue that this J symmetry has to do with the Lorentz symmetry in the target space. So we know the integrality structure. Using the integrality, we learn that the maximal state should be occupied. So therefore, we know what is the highest Lorentz spin on the winding string. But the winding string is dual to a graviton on the dual one. And there cannot be any spin more than 2 for graviton. So the very fact that the winding string becomes the momentum string and the spin cannot be more than 2, otherwise you get a massless mode which spin bigger than 2, and that's not allowed. We have the same spin. You get a bound on k, and you learn k is less than or equal to 1. So this is coming from T-duality together with the fact that the highest state has to be the graviton, but the central charge is related to the level, and you can get a bound on the higher charge, and you're done. So you find k is less than or equal to 1. K is less than or equal to 1 already implies C left is less than or equal to 24. Again. And C left less than 24 means what? Well, in d dimension, the degrees of the center of mass is d minus 2. So it's d minus 2 plus, you can write it as whatever it is. For example, if you write 24, is d minus 2 plus 24, d minus 24 minus d. So 26 minus d. Yes, thank you. I wrote this correctly now. Okay, 26 minus d. You learn that this is the center of mass boson at degrees of freedom, and this should be the bound on the central charge of the group, should be less than 26 minus d. And indeed, this is what we want, namely this is always bigger than or equal to the rank of the group. And so we learn that the rank of the group is less than 26 minus d, which is indeed consistent with what we have found there. Now, of course, it doesn't still finish the job to show you which discrete ones appear and which ones don't, but at least it gives you that all should be on the right of this, and already shows that there should be only a finite list. So already it is in the line of saying that infinitely many possibilities are not possible and they're gone. The same kind of story applies to n equals to 8 supercharges, which gives you the one with 4d n equal to 2 supersymmetry. Again, you have infinitely many lists. In that case, we use this unitarity argument on the strings. Again, it has strings. And using unitarity, we are able to cut the numbers. There are some infinite families that Waddy, Taylor, and collaborators found, which we can show it cannot be realized by unitarity. But they have other infinite families we have not ruled out yet. So there should be other ideas which presumably rule them out. But we have been only able to rule out some of them. So I think I'm running out of time. So let me just conclude by giving you actually one more set of examples, which actually shows the power of anomalies in these Swampland condition. And this is related to I think a very simple observation, which has actually deep consequences in quantum theory of gravity. So in the context of In the context of quantum field theories coupled to gravity, for example, we are familiar with the possibility of having gravitational anomalies, and global and local and so forth. And one of the ingredients of anomalies are deep connection with cobordism classes. For example, in d dimensions, when you're studying it, the fact that d plus one dimensional class of cobordism can host the potential gravitational anomaly is one of the key ingredients, and their vanishing or their class being trivial is an important ingredient. Here, I want to actually argue that a much more general statement that the cobordism class of a quantum gravity theory is 0 in every dimension. So quantum gravity is totally boring as far as cobordism class goes. This is actually one of the deep principles, I think, of connecting deep ideas of topology to quantum gravity. And it underlines a lot of these statements. And you might think, wait, something being 0, how could it be useful? It's very useful. For example, in the gauge theories, we have anomalies. And if gauge anomalies don't vanish, the theory doesn't make sense. Well, so if you have discovered some particles which don't have a vanishing anomalies, then you can predict there should be other ones which cancel it. Okay? The same here. If you define what do you mean by quantum gravity, and if you find and compute the cobordism classes, and you find it's not 0, it means you have not defined the category correctly. The category should be correctly incorporating some other objects that you have missed. And so therefore, this is going to teach you about new objects in the theory for which this vanishing appears. For example, if you have a gauge bundle, then you can define, if you have, for example, a field strength, then you have this trivial statement that df equals to 0, and this statement actually translates to a conserved chart. You can define a current which is star of f, and indeed d star j is 0, so you have a conserved current. So this would have given you a global charge, and this would be a problem with cobordism classes being non-trivial. This can give you a non-trivial class here if df is not 0, namely the Chern classes of the bundle. However, we know that we don't want to go. We are claiming this is not the case, which means that this cannot be 0. There must be some sources on this side. Things like monopole and so forth happens to do exactly that. In other words, the completeness of spectrum when you have gauge theory is related to triviality of the cobordism class. If you had the U1 theory with no charges, you would have extra global symmetries. That's not allowed. Global symmetries not being allowed is consistent with the ideas of Hawking with black holes evaporation, that you can throw in charges inside the black hole and they evaporate and they should disappear. And so, for example, in the context that we are talking about, so suppose, for example, you look at spin manifolds. The spin manifolds has a cobordism class. Omega spin, for example, in the fourth dimension is equal to z, and this is generated by K3. So you can throw a K3 inside the black hole. Now, what do I mean by that is that if you take a four-dimensional space and connect it to it a K3, and keep a black hole here, and throw a K3 inside the black hole, and wait till the black hole evaporates, you get rid of this class. So that means this class, which is represented by differential form as the first Pontryagin class, proportional to the Pontryagin class, should actually, the analog of the correct class should actually have a source contribution on the right side, even though the Pontryagin class is naively classically conserved, which means that there must be some new singularities allowed in quantum gravity to kill this class. So the power of anomalies is all over the place. And so this, for example, predicts the existence of five-dimensional trivialization of K3, something whose boundary is K3, and it's somehow allowed. And what kind of singularities there are which does this, we haven't figured out exactly, but anomaly predicts there is such a thing. Moreover, this five-dimensional object is going to be non-supersymmetric. You can show that. So the toolkit of supersymmetry is not smart enough to construct this answer, but anomaly is smart enough to predict that there must be one. So anomaly goes beyond supersymmetry in this case, and that's quite elegant, that anomaly actually takes over supersymmetry as the leading role in trying to predict some new features. And indeed, this is quite exciting because the triviality of any compactification in string theory, if you look at the downsides, if you take manifold and if it's trivial, it simply means that any quantum gravity in lower dimension should allow a boundary. That means in our universe, right now, with whatever structure of supersymmetry we have or we don't have, we should be able to have a void. We should have a boundary of the manifold, including a bubble of what we call nothing. So you can have a boundary with nothing in it. So this is quite remarkable, and more than that, you can connect any one to any other one. You can put two bubbles together, and so you should be able to go from any quantum gravity to any other one that you like. If you like a Calabi-Yau compactification, you should be able to create a bubble in our universe now to go to that one, perhaps behind the horizon of a black hole. Again, follows from the triviality of cobordism classes and anomalies. So there I start. Thank you.
So it's very wonderful to have only finitely many possibilities, but is there one that resembles nature?
We hope so.
So, but it's not clear yet.
It's not proven yet, no. But I think that it's clear to string theory practitioners that there must be one, but that's not good enough. We have to construct.
Cumrun, so your basic argument is based on the string being part of the spectrum, what you call the complete spectrum principle or something. But if you assume this, isn't it tantamount to saying there's a fundamental string and then you are back to string theory?
Well, I'm using string theory as examples of consistent quantum gravities. There could have been other ones.
Yeah, but your anomaly argument used the string.
No. So just to make it clear is that I didn't get a chance to talk about the dance with 8 supercharges. That's in 6D. In that case, you find that there are many strings, not just one string. There's a lattice of strings. And I pick the right string for each one of them. So it's not the fundamental string. I'm not looking at fundamental string. It happens in the context of so much higher supersymmetry, there's a canonical string. But in the general case, there is no canonical string. And I was using that. So it's not a string theory. The argument I used was the existence of a string like a black brain, if you want to think about it like that. An existence of a solution to Einstein's equation.
Yeah, but if there is a regime in which you can quantize this string, you are back to string theory.
I never assumed that. So let me be clear on that. The anomalies on the string has nothing to do with whether the quantization of that will give you the fundamental theory. All I'm saying is that there's some defect living on it, which I can describe, see left and see right, and you can flow in the infrared of that defect and see whatever you get. I'm not thinking that gravity is following from interaction of that at all. In fact, it may have nothing to do with it, and in some cases has nothing to do with it, like in 6D case that I'm talking about. It is not the interaction of these strings will tell you anything about the quantum gravity per se, but it's smart enough to know that. Now, this is just strings. Of course, it's natural to talk about other defects, 4-dimensional defects, 5-dimensional defects, 6-dimensional. These are definitely worthwhile studying, and we've just started that kind of program. So the idea that defects cannot be forgotten, and they're part of the ingredient, kind of bootstraps the gravity, supergravity, to a bigger structure, which must be much more restrictive, and that potentially could be fitting more along the lines of restrictions we see in string theory. That's the idea.
Actually, I have follow-up to Costa's question, frankly. 10 dimension is special here, because once you have a string in 10 dimension, it flies in 10 dimension, right? Now the question is, target is 10 dimension. The question is it a critical string? Because you have supersymmetry is right amount. Now it's close. I mean, it's difficult to. I had some paper with Ruben and Pierre Van Hoff. If it's closed string, right? It flies in 10 dimensions. It has this many supersymmetry. It has massless spectrum in 10 dimensions. And then you look what is the massless spectrum 10 dimension. Actually, it's the same thing that you started with, right? Because it's either E8 or essentially. So suddenly, if it's in 10 dimension, it's because of critical. You had, in the beginning there was no string theory, then you have this now string, it flies in 10 dimension, and once you get this stuff back.
Yeah, so let me explain again more. I'm not talking about quantization of the string in the sense of fundamental string. No, because what I'm trying to say is that C left and C right are not zero. In string theory, they are zero. I'm talking about infinitely long string.
It's a long string.
Infinitely long string. It's not the usual tiny strings we usually do in string theory. Of course, you could say, well, if I take fundamental string and stretch it like this, that would be more like the one I'm talking about. That's why the center charge is not zero.
Okay. Going back to your example with the brains and localized gauge theories on them. So, well, presumably I can cancel Ramon charge. I don't know why. That's a question.
Yes.
And compactify.
Yes.
If that's possible, then at low energies you would still have a consistent theory, I suppose.
Yes.
Right? So then your statement about low energy quantum gravities
Yes.
is actually a statement about the unit completion of those.
Yes, exactly. So for example, that's a good way of asking it. For example, D3 brain if you have this infinitely many D3 branes, there's no problem in the bulk because the Ramon flux for them can go to the bulk. But if you had compactified, that would correspond to a charge in a compact space. You cannot have it. Of course, if you have orientifold, you can have a finite number, a few more you can add by orientifold to cancel the orientifold charge, and that's it. But there's just a few of them. So that's the bound. So that's exactly the idea. That is, once you have a restriction based on compactification, you get these restrictions. And in fact, that's a mathematical language. Compact versus non-compact. Non-compact things, you get infinitely many possibilities. Compact is finite. And that's a quick mathematical summary of what this kind of thing suggests.
Any more questions? Yeah. Actually, I have some remarks.
Yes.
It's about fountains of Calabi-Yau. It's also a very general idea of Gromov about if you have boundless of diameter, dimension, and low boundless of Ricci curvature, then you have kind of compactness of the whole story. And I think that's a real reason to believe that they are finite. Not just because you have kind of finitely many things you can build.
But is there some upper bound that you can actually give using this? For example, can you give for example, a bound on the Euler axis of Calabi-Yau threefold?
No, it's more questions that if you get kind of like singularities, it's not effective bound, but it's roughly, it's kind of a rough idea of compactness. And
yeah, it would be great to quantify, to better understand that principle mathematically first and then perhaps physically, because we don't have a good understanding why. I mean, it's kind of comes, but this is a key principle. If there are only finite number of quantum gravity things, it's a great thing because we know we are blessed to be having a quantum gravity in our universe, so therefore we are part of that finite set, and that will actually be quite the opposite to saying, oh, there's this infinite landscape, there's nothing. This is actually quite the opposite.
So anything you can say if there's no supersymmetry?
Yes, we do have non-supersymmetric things, and there are parts of the Swampland program which have to discuss what happens to supersymmetry, implications for cosmology, and so on. So it's very difficult, and in fact, we think it may even be impossible to get stable positive energy in the context of string theory. People are still debating it, so it's not settled yet. But for example, one thing we know is that if you take a space of these scalar fields, the potential that you can get now, since you break supersymmetry, you can have potentials. And far away in the distance in marginalized space, the potential always vanishes. And vanishes exponentially fast with distance. Why and so on, we don't have a deep understanding. We have understanding from string construction. So people have conjectures about how this exponential behavior comes about and so forth. So people have come about with new ideas with breaking supersymmetry. And so precisely those kind of questions are potentially very interesting for cosmology. And that's one of the areas I'm most interested in, applying these to cosmological setup.
Eventually you don't want to use string theory, I suppose.
I'm not using string theory. I'm using principles I learned from string theory. And examples from string theory guide us to what are the correct principles. That's the way I look at it.
But then you could turn the argument around. You could say if it doesn't fit our low energy theories, then maybe the string theory was not a good setup to start.
Well, we don't know enough about low energy, what precise low energy we are in. Cosmologically, we still are debating what are the possibilities. And I mean, from all the evidence we are learning, is the fact that string theory actually is the only game in town. I mean, I was trying to give you these examples that didn't have to work. None of them had to work. It's working, so why? And it's not because this is just a finite small set we were doing. We're just using classification of supersymmetries, and somehow string picks them exactly right in very non-trivial ways.
Okay, yes. There's the last question, yeah.
Can you give some example of a theory of quantum field theory which has completely broken supersymmetry but stays conformal?
You mean with gravity? There's nothing conformality, of course.
On the gauge theory side.
Well, there are conformal theories, for example, in 2D, which have no supersymmetry, and there are even in 4D. 4D, people have arguments. For example, Bank-Zaks kind of construction suggests. Well, so there are examples. If you're asking if there are examples, I'm saying there are. If I know all the examples, no, I don't know all the examples.
Or even more precise statement, do you have it in higher than 4 dimensions, but with spontaneous symmetry breaking? I mean, with flat vacuum.
Spontaneous symmetry for the gauge theories you're asking?
Yeah, say quantum field theory. Conformal with.
Well, why is this related to this topic? I'm not getting the connection to what I'm talking about. It's an interesting question, but what's the relation?
You classify the quantum field theories also.
No, I didn't classify quantum field theories. I was mainly talking about quantum gravity theories, which which are consistent to ask which quantum field theories it leads to. That was a different set. The set of quantum field theories is infinite, clearly, and there are, with or without supersymmetry, it's infinite. There's no doubt about that in my mind. The question is which ones arise as good ones within gravity, which ones can be coupled to gravity, and that's the one I'm saying is only a finite number of them. It could be that we know with no supersymmetry, we don't know which ones would even be a stable vacuum. And it's possible, and I suspect the answer is there are no stable non-supersymmetric ones. So therefore, this question becomes a bit strange in the context of gravity. What do you exactly want? So that's not quite well posed. In other words,
within the ideal CFT correspondence, if you ask more this question, if there's a conformal theory
that's not the one he was asking, but yes, you could have asked that question. In which case, I would say that there are some no-go conjectures, at least, for the context of what do you mean by non-supersymmetric ADS-CFT type correspondence. That we think that there might be some troubles with the weak gravity conjectures in that context, if you take the weak gravity conjecture and strengthen.
I think we are a bit late, so speak again.
Thank you.